In this, we're gonna review the volumes by the washer method. So washer method applies when the cross section has a shape of a washer. So what we're gonna do, we're gonna find the two radii and then find the area of the washer, um, and then integrate that. So let's uh, look at the technique. So we're gonna start with the graphs, two graphs. So let's say, so we need two graphs now. So what's gonna happen? So let's say we have these two graphs. So this is one, and let's say this is the other one. Okay, two graphs. So the first one we can call it y equal fx. The bottom one we're gonna call y equal gx. So what we're gonna do for simplicity, let's talk about the rotation around the x-axis. So we're gonna rotate this region. So let's talk about this region. So we have region. We it's gonna start at A and go all the way up to B. So that's the region we have. So what we're gonna do? We're gonna rotate this around the x-axis. What's gonna happen? It's gonna reflect to the other side. So so you're gonna get a curve like that. Uh, yeah, I'm gonna graph it. Uh, so that's A. That's the other corner. And then we have the other graph that's also going to reflect like that. Good. So that's what happens when you reflect it, when you rotate it. So so what's the shape of the cross section? So you can see can go like that. Now when you look at the cross section, so you can see that it's gonna look like a washer. So if you cut it, you're gonna see like part here, the other part over there. You can see that the part in the middle is missing. So then we have two radii. So if you measure the radius from the x-axis, so we're gonna measure the radius from the axis of rotation. So that's the important part. So we're gonna measure this distance. So we have a larger radius. We have always two radii. So we have larger radius. I'm gonna call uppercase R, and we have a smaller radius. I'm gonna call lowercase r. So let's use that convention. We always use R, uppercase R for the larger one, small r for the small one. So like that. And it doesn't matter where you're going to measure it, whether it's from the top or the bottom. So always try to use something easy to manage, because some curves we don't know. So in this case, we know the curves from the top. So we're going to use the data from the top curves, because we know the two curves. Bottom curves is a minus of fx and minus of gx. So you have to be careful which one we're going to use. Okay, so I'm going to use the top curves. So it doesn't matter how you get it. Okay, so now, so that's the situations. We have a small r and a large r. Um, Sometimes we can also call it the 1 and 2 just for reference purposes. And then we can see the larger r is simply the y coordinate of the top curve. So that means which is fx. And the small r, which is the y coordinate of the bottom curve. So it is gx. So those two are the two curves, fx and gx. Okay, that's the first thing to notice. What is the r? A large one and a small one. And then you can also see that this problem is a dx problem. So you can see these gaps. The thickness is a dx problem. See, thickness is or delta x. You can call delta x. So that means that's going to give you a clue. That means everything has to be in terms of x, because that's the thickness. Okay, so everything we can write in terms of x. So that's why you write the two radii in terms of x. So you can see it's very clear now. It's a function of x and function of x. So that's one important thing. Okay, now so if you look at the cross section, how the cross section looks like, you can see the cross section looks like this. So this is from the larger radii radius. This is from the smaller radius. So it's gonna look like that. Um, so so the so area. So these are two radii. So this is the small r that we mark up there, and this is the larger one. Um, okay, those are the two radii. So what we need to find is the cross section area. So we need to find this area. Okay, we need to find this area, and you can see that. this is like we can use simple geometry here, call it geometry. So it is pi large R squared minus pi small r squared. So that's going to give you the radii, or if you can take pi out, so it is r squared minus r squared. So that's what you get as the area of this one. And if you also see in a different point of view, so you can see this looks like this. So that is the disk, go like that. These are the circular disk. Um, Yeah, so this is how it looks like. So, so you can see, so this is the thickness that we are talking about. So I'm gonna mark it like that. So that's the thickness. That's the dx part. Okay, that's the thickness. So it looks like a cylinder. So that's the thickness. So this is we can call it dx. Okay, dx. That's the thickness, and that's the area we were talking about there. So that's the same area. So to find the smaller volume, so that's that. That's the same one. Uh, so to find the smaller volume, what we can do is we can multiply by the area um, with the height. Because it's like a thick cylinder with a hole in it. So but we know the area now. So it's the area times width. So so that means we can write this formula. So the volume uh, equal, so you can say it is a to b ax dx type of problem, but you can translate that to a to b, whatever the limits, pi. You can see we find the area, which is r squared minus r squared dx with the thickness. So that means as a final answer, you're going to get, I mean, we can write this out. So a to b, so it is simply r squared minus r squared. Large R squared minus small r squared. So remember like that, because the large R means the large radius, small r means small radius. So that is the formula we are talking about. Okay, good. And then also one thing that we need to remember, when we do this one, we're gonna cut a perpendicular to the axis of rotation. Okay, that's an important fact. Uh, so you're gonna cut a perpendicular to the axis of rotation. Axis of rotation. Okay, so that's the formula. So there's only one formula. So let's do a couple of examples just to understand the concept. So what we're gonna do, I'm gonna use just one region, but four different axes. Then you can see how you use them in a different situation. Okay, just uh, one region, four axes. Okay, let's do that problem. So example number one. Okay, so the problem says find the volume of the solid generated by rotating the region enclosed by these two curves, y equal x squared and y equal square root x, about the given axis. So let's talk about few different axes. As the first example, let's talk about the x-axis. So let's rotate about the x-axis. So let's graph the situation. So we have two curves, and these are two familiar curves. One is y equal x squared, that has a shape like that. The other one is y equal square root x, that has a shape like this. So those are the two curves. And then we also know that these two are going to meet at the point 1. At 1 they are the same, and then also you get the value 1 in the y-axis. So these are the information that we have. So now what we're going to do, we're going to rotate in this case about the uh, x-axis. We're going to rotate about the x-axis. So once you rotate about the x-axis, what's going to happen? This is going to reflect to the other side. So you're going to get the reflection. So you're going to get the reflection on the other side. So you get this, and then you can see. Now what we're going to do is we're going to cut it perpendicular to the axis of rotation. So you're going to get a simple washer like that. So this is how we look at it, top and bottom. But you only need one part for the data. So what we're going to do is we're going to find the two radii. So we need the larger radius and the smaller radius. So let's go with the larger radius. So that is the larger radius. r, and the smaller radius that. And you can see that those radii are simply the y coordinate. Okay, so I'm going to call the first graph, let's say uh, y, we can say y1 for reference purposes, that is square root function, and this is the y2, so that is the x squared function. I'm going to call y1 y2 for references. Okay, now what we're going to do is to find the two radii. So let's start with the large radius. So the large radius is y1 coordinate, which is simply square root x. The smaller radius is the y2 coordinate. It's just the y coordinate of the function, which is equal to x squared. Okay, that's what the formula says. So we know the two radii now. That's the first step. And what we're going to do now is we're going to plug in that to the formula. So we know that the volume is, according to the formula, which is pi a to b large r squared minus small r squared dx. And you can see this is a dx problem because we're going to cut perpendicular to the x-axis. So it's a dx problem. The thickness is dx. Good. So now we're going to plug in here. So we have pi, and then what are the limits? So you can see the x limits going from 0 to 1. Okay, so it's clear. So this is 0 to 1. So it is 0 to 1. And then let's plug in. Large R is square root x, so it is square root x squared, square root x squared minus small r is x squared, we square that too. So that's what you get. So that is the formula. So if you want to set up the formula, you're done. That's the formula. But we're going to complete the problem. So what we're going to do, we're going to simplify. So how to simplify? You can simplify this. So you're going to get, when you square this one, you're going to get x minus x to the fourth dx. So this is a very simple integral. So it is x squared over 2 minus x squared over 2 minus x to the fifth over fifth, and then we can evaluate at 1 and 0. So if you plug in evaluate at 1 and 0, you're going to get 1/2 minus 1/5. A common denominator is 10. 5 goes there, 2 goes there. So how you simplify? So you can see the 5 goes this way, 2 goes that way, and then subtract. So that means you're going to get 3 in the top and 10 in the bottom. So it is 310 pi unit cube, because this is a volume. Okay, that's about that. So let's do part B. Let's now pick the same region. So we're going to pick the exact same region. So that's the region. But now we're going to rotate this about the y-axis. Okay. So B, the y-axis. So so we get the same graph now. So and then again it's 1 and 1. So this is the y-axis. So we get rotated about the y-axis now. Okay. So what's going to happen? This can reflect to the other side. So you get this. And then what we can do, we're going to cut perpendicular to the axis of rotation. So that's the y-axis. So if you cut it perpendicular to axis of rotation, so you a typical cross section looks like that. And then what we're going to need is we're going to find the radii. Use any side you like, but it's clear that if you use the first quadrant, that's much easy to find the radii. So you can see, so I'm going to mark them. So this is the large radius. So this is smaller radius first, and this is the large radius. And you can see that those are equals to the x coordinate of those two curves. So so I'm going to mark these two separately. So this is the small x coordinate. I'm going to call x small r, and this is the larger x coordinate. I'm going to call x r like that. Okay, so that means you can see the thickness is on dx, it's a dy actually. Thickness is going in the dy direction, so it's a y direction. That means you need to write everything in terms of y. Okay, you need to write everything in terms of y. That means you have solve for x, because then you can remove that. So that means so we can start with the two curves. So we have x, we have y equal x squared, that's the first one. uh, y equal square root x, that's the first one. And then this says that x equal y squared. So that is that one. So you can write this one as x equal y squared, and the other one is y equal x squared. This says that x equal square root y. That's this one. Okay, so this is gonna give you the two coordinate x small r. Actually, if you want to put that reference, that is the smaller r, that is the large r. Okay, those are the references if you want. Now what we can do is we're gonna find the two radii. So we can write r, the large r. So the larger r is in this case uh, xr, so which is equals to square root y, and the small r, which is x small r, which is equal to y square. So you can write it like that. So those two are the so we express the radii in terms of y. Now what we need to do is write the integral. So v equal pi, so this is a y integral, I'm going to cd, and then large r squared minus small r squared dy. So we can plug it. So let's plug in. So it's a pi. The limits are going from, now we need the y limits, and you can see that the y limits also 0 to 1. So 0 to 1. Now let's plug in the radii. So what are the radii? The larger radius is square root y. So it is square root y, it is square that, minus the small radius is y squared, you have to square that too. So and that is the setup of the integral. So this is like easy to simplify as before. So it's a pi 0 1. First one says y, the second one says y to the fourth dy, and you can see that this is exactly the same integral from the last time. So that means we know the answer for this one. So answer was 310 pi. Okay, that doesn't happen always. This is a special situation. The reason is when you transform from x integral to y integral, what happened? They switch the curves. So that's the reason. So this is the extra step we need when you do y integrals. So when you do y integrals, you always need to solve for x first. Okay, so this extra step we need when you do y integrals. So I'm going to put extra step, step for y integrals, for dy integrals. Okay, so if you have a dy integral, when you do the washer or the disk method, you always need to solve for that. So we have that extra step in this case. Okay, so that's about that. So let's talk about the next case. Let's rotate about maybe like x equal negative 1 axis, the same region, but x equal negative 1 axis. Okay, so what's the region? That's the region you're talking about. You can see the exact same region, but in this case you get the exact same answer, but that's a coincidence, okay, because they switch between the two curves. Okay, so let's talk about another axis. So C, so let's do x equal negative 1 axis. So you can rotate the same region about the x equal negative 1 axis. So we get the same graphs, and they meet at 1. So 1 and negative 1 and 1 as before, the y-axis and the x-axis. So what we can do now is we can rotate this about, okay, this is not in scale, so I'm gonna rotate about negative 1 axis. So that's the x equal negative 1 axis. So that's the axis of rotation. So we can rotate about that. So what happened is going to reflect to the other side. And then look at the cross section as before. So we're going to cut perpendicular to the x-axis, to the x equal -1 axis with x-axis rotation. So you're going to see typical cross sections like that. Now as before, what we're going to do is we're going to find the two radii. So let's pay attention to this situation right now. And so you can see, so it's you can rotate about this axis. That means you again need to find the x coordinate. So you need the 2x coordinate, you need the x values here. So I'm going to call the value corresponds to small r, that's the x small r, and then so that's the x small r, and also the value corresponds to large r, so that's the value corresponds to large r, xr. So actual radii are different, so you can see, and then also you notice that this distance is 1. Okay, this not -1, the distance is 1. So that means if you want to find the radii, the larger radii, so what you want to do is this is the larger radii, and it's going to be simply 1 plus that whatever the distance. So you can see in this case larger radius xr, so you have to add 1 to the xr. That's how you get the larger radius, and the smaller one is also the same. So that means the smaller radius, so the smaller radius, uh, so which is going to be 1 plus x small r. So that's how you get the two radii, because it's always 1 plus, because you're going to measure from 1 to those two ends, okay, to the large radius and the small radius. Okay, so let's try the rest of the calculation. So you can see the first thing that we did, we solve for the two curves, and then we can write it. So this is x equal uh, square root y. This is x equal y squared, because you solve for them. You solve for x in the previous problem, so I'm going to use that fact here. So now we have the two radii, so r equal 1 plus x small r, so which is 1 plus x small r is, you can see it is the top curve, so it's y squared, so 1 plus y squared, and the large r, which is 1 plus x larger x coordinate, which is 1 plus square root y. Good. And then we get the volume formula, so the volume is pi, so we can write the values. It is okay, and then you can see this is a dy problem, so that means we need the limits of y limits. So what are the y limits? And you can see that it's again go from 0 to 1. So those are 0 to 1. As before, it's a larger r squared minus small r squared dy now. So that's the important part. Okay. So it's clear now, we hope. So it is pi, so let's plug in. So it is 0 to 1. So we have large r is 1 plus square root y whole thing squared minus 1 plus y squared whole thing squared dy. So that is the setup of the integral. Okay, if you just want to set up, that's where you're going to stop. But since this is the problem of this type, first problem, so I'm going to complete the whole problem. So let's do it. So what's the next step? You can see you can distribute inside. So if you distribute, what do you get? So it is pi 0 to 1. So let's distribute. So if you distribute in the from the first one, you get 1 plus 2 square root y plus y minus, from the second one 1 plus twice the product plus square of that. That's what you get, dy. And you can see there are some simplification, the term is gone, so you end up getting pi 0 to 1. So what do you get? So let's write from the first one. So we have y plus, so let's start with the smallest one. There's no order, you can write in any order. I normally write the positive one first, so 2 square root y plus y minus 2y squared minus y to the fourth. Okay, so now what you can do, just integrate term by term. So if you integrate, you're going to get from the first one, you're going to get 4/3 y 3/2, and then y squared over 2, and then 2/3 y cube plus 1/5 y fifth. Evaluate at 1 and 0. When you plug in 0, is gone. When you plug in 1, you get numbers, and you can see actually what you get, pi. You get 4/3, 1/2, 2/3, 1/5, and if you simplify all of them, you're gonna get 2930 pi. So that's the volume of the solid generated. Okay, so let's do as the last one. Let's do one from another axis. So I'm going to do the d-axis. I'm going to do like a y equal 2. So let's do y equal 2. So write it about y equal 2. So the same region. So that means we're going to get these graphs. So they again meet at 1. When you plug in 1 is 1. And this is so the axis of rotation is this one. So it's going to go through y equal 2. That is y equal 2. So we can rotate about that. So that means it's going to jump to the other side. And then what we're going to do, we're going to cut perpendicular to the axis of rotation. So that means we're going to cut it like this. So we're going to get this. Okay. Now again, so it doesn't really matter which curves to use, but we know, like, in the bottom we actually know the curves, and then thickness is dx. So that's the dx. That means everything has to be in terms of x. So this is 0. So, and then what do you want to know is, and you know this distance is 1. Okay, so that's one of the not 1, it's 2, because you rotate about 2 axis, so that is 2. So what do you want to do? You want to find the 2 radii. So what are the 2 radii now? And you can see that this is the smaller radius. I'm going to write on the other side. Yeah, that's fine. That's a small radius, and then this is the larger radius. So those are the 2 radii. So what you want to do is we need to find a way to find it, but you can see that you can use the y coordinate to find them. For example, if you know this y coordinate, so I'm going to call this is y1 for reference purposes, and this is y2, and you can write a formula now. And then what are those 2 curves? And we know that this is the y equal x squared, and this one is y equal square root x, and we can use those 2 coordinates. So that means this is y2 and this is y1 as reference. Okay, so that means according to this information, then we can write the 2 radii. So what's going to happen? So what is small r? You can see small r is 2 minus y1, 2 minus y1. It's very clear from the geometry. Small r is 2 minus y1. So but y1 we know. So what is y1? Y1 means square root x. Okay, y1 means square root x. So it's a 2 minus square. Okay, so 2 minus square root x. And the same thing we can do large r, that is 2 minus y2, which is 2 minus x squared. Okay, so we find the 2 radii. Now what we can do, we're going to plug into the formula. So it is pi 0 1 large r squared minus small r squared dx problem now. So let's plug in. So we have 0 1. Large r means 2 minus x squared, and then the small r is 2 minus square root x. You have to square that, and then dx. So that's what you get as the formulas. That's a setup of the integral, and then you can finish it as before. So I'm going to skip some of the steps. So once you simplify, you should end up getting this x squared minus 4x squared minus x plus 4 square root x. That's what you get, dx. And then once you integrate, you're gonna get 31 over 30 pi. Okay, see whether you get this as the answer. Okay, this is how you handle a problem with different axes. Okay, so what I will do is, so that if you familiarize with those 4 examples, you can pretty much do any problem of this type. So what I'm going to do, I'm going to give you a few extra problems for you to see. But what I'm going to do, I'm just going to set up the integral. I will not, and let's keep the simplification later. But you can find the final answer in the description. Okay, so let's look at these problems. So what we can do, we're going to set up the integral for several different curves. So the problem says set up the integrals for the volume of the solid generated by rotating the region bounded by the given curves about the given axis. Okay, so let's talk about as a first example this one. So the region is y equal square root x as bounded by y equal square root x, y equal 2, x equals 0 about the x axis. So let's graph them first. So we have this. So we're gonna have square root x. So that's the square root x function. So and then y equal 2. So that's the y equal 2. And x equals 0 axis. That's x equals 0 axis. That's the y axis. So that means this is the region they are talking about. Okay, so that's the region. Now what we can do, we can rotate this about the x axis. So and then this is 2. So if this is 2, this is square root function. So that means so this has to be, so the square root function, so y equal square root x function. That means this has to be 4. So we can look at the radius. So that's the radius that we need. So we need the larger radius and the smaller radius. And you can see that so this is the smaller radius, and that is the larger radius. And you can see that the larger radius is simply equals to 2. That's a constant throughout, and the smaller radius is simply the y coordinate. Y coordinate means square root x. Okay, so that means the formula is pi. The limits, because it's a dx problem, so that means the x limit, so it's 0 to 4. So we can have a larger radius squared minus smaller radius squared dx. So that's the setup of the integral. Okay, so next to this one, so you can see it's the same region, y equal square root x, y equal to x equals 0, but now about the y equal 2 axis. So so let's graph the situation. So the axis is this one. So this is y equal 2 axis. So what happens is gonna reflect to the other side like this. So now what we need to do is we need to mark the radius. So you can find the radius from any side you like, but you can see if you try to find the radius from the bottom, it will be much easier. So we're gonna find the radius from the bottom because we already know the curve. Because if you use the top one, we don't know the curve. So we have this y coordinate. So that's the y coordinate. So now you can see that this is not a washer problem, because you can see here, you can see the complete disk now. So there's no hole in there. So that means we don't need the disk. Actually, this method is a washer method. The internal radius is 0. So and then this is the smaller radius. So we still need to find this radius. So it is just the radius now. So what's the radius? So you can see that this length is 2. So the radius is simply becomes 2 minus the y coordinate. So right, radius is simply 2 minus the y coordinate. That means 2 minus the y coordinate is square root x. That's what have. So it's not really the washer method, but you can say it's a washer method, but it looks like a disk. So we can write the volume formula. So it is pi, the x is a dx problem because the small thin disk move in the x direction, even cut in the x direction. So it is going from 0 to 4 again. Uh, so uh, and then it is r radius square dx problem. So it is pi 0 to 4. Radius is 2 minus square root x squared dx. So and you can see the internal radius is 0, so you don't see any term. So this is a it's a washer, but it looks like a disk method. Okay, so it looks like a disk method. This method is a subcase of the washer method. Okay, so but that's the setup. Okay, so let's look at a different curve, like a sine curve now. So the problem is y equal sine x, y equal 2, x equal 0, x equal pi over 2. So those are like we have 3 lines and 1 curve about x-axis. So how it looks like? So you're gonna get this graph. Um, so we have the x-axis. There is a sine curve. So what's gonna happen? You're gonna rotate about the x-axis. So what's gonna happen? This is gonna jump to the other side. Um, so where's the region? Region is the sine curve y equal 1. So you can see this exactly. There's a y equal sine and the y equal 2. X equal 0 is the y-axis and the other one is x equal pi over 2. So this is x equal pi over 2 and this is x equal 0 axis or the y-axis. Okay, so that means the region you are talking about is this region. So think about the curve, the top line, which is y equal 1, the top line, and we have 2 lines on the other side, x equals 0 and x equal pi over 2. So that's define this region, and then you can rotate that region around the x-axis, so it's going to jump to the other side. So that means so this region is sitting there now. So that's the reflection of that. Good. So as before, what we need is we need this radius. Uh, we need the large r and the small r. Uh, and then we know this is a sine curve, so this is the small r. That's just the y coordinate. And the large r is simply equals to 1, which is fixed. So large r equals to 1, small r equals to the y coordinate, which is simply the sine x. So then we can write the integral. So v equal pi, the limits. So I'm gonna write it. So it's a to b r squared minus r squared is a dx problem. So let's plug in. So it is a pi. We have 0, pi over 2. You can see x coordinate, x going from 0 all the way up to pi over 2. Good. So the larger radius is 1, so 1 squared minus smaller radius is sine, so it is sine squared x. So that's what you get dx. And you can simplify if you want. You can see this is simply cosine squared x. And so that is the setup of the integral. And to do this integral, you need to know the trigonometric integral technique that we discussed under that section. Okay, so that's the setup. So let's do the next one now. Let's rotate about a different axis. How about we rotate this about the x equal pi over 2 axis. So we have y equals sine x, y equal 1, x equal 0, x equal pi over 2. That's the same region, but now it's about the x equal pi over 2, x equal pi over 2. So let's graph the curve. So we have this. So now what we can do, we can rotate this about the x equal pi over 2 axis. So that's the axis of rotation. So this is x equal pi over 2. So what happened when you rotate about that axis, it's going to jump to the other side. So you're going to get this. So this is the region reflected. So this region is going to reflect because you rotate about this axis. So it's going to jump to the other side. That's what you get. Okay, so now what we need to do is we need to find the radii. So again, so we're going to cut perpendicular to the axis of rotation. So here this is the x-axis, this is the y-axis, and this is where we rotate, so pi over 2. So it's going to jump to pi. Now, so we're going to cut it. So when you cut it perpendicular to the axis of rotation, so we need, this is the one we need. That's the small cross section. So it's a dy problem now. It's not a dx anymore. Good. So it is a dy problem. That's the thickness, which is a dy. And the limits go from 0 to 1 here. Good. So what we need to now is we need to know the radii, but you can see where's the radius. You always measure the radius from the axis of rotation. So that means this is the smaller radius, and this is the larger radius. Okay. So what we're gonna do is so you're gonna look at the x coordinate. So that's the x coordinate. So that's the x coordinate. So you can use that to find those radii. So you can see this length is pi over 2. So we know this length, which is pi over 2. So you can use that to find the radius. So you can see the larger radius, let's say smaller, easy one. So the larger radius is fixed, which is pi over 2. The smaller radius, so you can see when you want to find a smaller radius, you need the x coordinate. So that means you have to solve for x. So we're going to start with that when you do a problem like that. Okay, so we have y equal sine x. So that means so this says that x equal sine inverse y. Okay, now we have the larger radius, which is pi over 2, and then we have the smaller radius. You can see smaller radius is total length is pi over 2 minus the x coordinate. That means pi over 2 minus sine inverse y. Okay, that's what I get. Okay, so we have two radii. Now we can write the formula. So the formula V is again it's pi. The limits go from, okay, these are the y limits. So the y limits go from 0 to 1. Okay, the y limits. So go from 0 to 1 with the dy problem. That's the reason why we need that. You have to write everything in terms of y. Good. And then so we have the large radius is pi over 2, so you square that minus smaller radius is pi over 2 minus sine inverse y squared dy. Okay, so that is the setup of the integral. Good. Then let's do one from natural log and another from exponential function. So let's do the natural log one. So we have y equal ln x minus 1, y equal 1, x equal 2 about the y equal x axis. So let's graph this. So you can see that this is not a difficult graph. So we're going to start with the axis. So what happened here is this is not just the ln graph, but you have to shift that by 1 to the right. So that means normally the ln graph passes through 1, but since we move it, this gonna passes through 2. So that means this is the graph you get. It's gonna go like that. So and then we have y equal 1 line. So that's y equal 1 line. And then we also x equal 2. So we know that that's exactly passed through 2. So that means that's the other line we are talking about. Good. So, and then this is the region. Okay, so that's the region. So we can rotate this about the y-axis. So you can rotate. So this is the x-axis, and that is the y-axis. Uh, so this is the line 1. So this is y equal 1 line. So this is the graph y equal ln x minus 1. Okay, so we're gonna cut it. So we're gonna rotate about the y-axis. So that means we're gonna cut it perpendicular to that. So that means the small cross section looks like that. So it's gonna jump to the other side. Good. So what you get is this simply. So we get that. Okay. So and that's the other side. So when you do problems like that in the exam, you don't want to draw all of them. You only need to find the radius correct. Okay, so and then you can see that so this is the large radius, and this is the smaller radius, and you can see this is the x coordinate for r. Okay, you can see smaller radius is simply 2 in this case. Okay, good. So let's write everything we need. So you can see that you need to, it's a dy problem, so that means you have to solve for x. So we have y equal ln x minus 1. So this says that x minus 1 equal e to the y. In other words, x equal 1 plus e to the y. Good. So that's the x coordinate. So then now we can write the two radii. Smaller radii is simply 2. That's the fixed gap. The larger radii is simply the x coordinate. So x coordinate in this case is equals to 1 plus ey. Good. So then we can plug in the numbers we have. So we have the formula now. So we can say v equal pi, the limit going from 0 to 1, y limits, this is the y limits, and then the large radius is 1 plus ey whole thing squared minus the small radius is 2, so we have dy. So that is the setup of the integral. So yeah, and then it's not that difficult to integrate this one. So as the next one, let's do one from exponential functions. So the problem is y equal e to the 3x, x equals 0, y equal e to the 6, about x equal negative 2. So we're going to get these graphs. So this is the shape of the graph, e to the 3x. So what are the numbers we have? We have 0 and this pass through 1 that we know. And then, so this is e to the 6. So the line is y equal e6. So if the line is y equal e6, so this is the line y equal e to the 6. So this is e to the 3x, that means this has to be 2. So this is 2. And then you can see this, we can rotate this about the line x equal negative 2. So that's the line. So we can rotate about this line. So this is x equal negative 2. So that means this distance is 2. So we have this distance which is equal to 2. Okay, so so that's the region. So it's going to jump to the other side when you rotate it. So what we need is a typical two radii. So this is the how the cross section looks like. So we define the two radii, and you can see that this is the smaller radii, which is r, and the larger radii. So if you say this is the x coordinate, so this is the larger radii. Okay, so the larger radii is 2 plus the x coordinate. Okay, so that means we have to solve for x coordinate. So we have y equal e to the 3x. So if you solve for x, you can see 3x equal ln y. So x equal 1/3 lny. So that's what we have. So, and then you can see the smaller radius is 2. The larger radius is 2 plus the x coordinate. So that means 2 plus 1/3 lny. So we can have the formula. So v equal pi. So we have okay, what are the limits? So you can see it's the dy problem. So in the y limits, so go from 0 to not 0. It's starting with 1 because that's where the y start. So you have to be careful and go up to e to the 6. So it is 1 to e to the 6. So that's very important. It's 1. And then the larger radius is 2 plus 1/3 lny squared minus 2 squared dy. Okay. So that is what you get as the setup of the integral. So let's do one last problem, which may be a little bit difficult, but it's okay. Just try to see what happened. Okay, so this is the last one. Uh, Let me start here because it's like a difficult problem. So the problem is y equals sin x, y equal 1, x equal pi over 2, and x equal pi about the y-axis. So, so what is the region? So let's draw the region first. So we have the x-axis, y-axis, and the curve. So this is pi over 2 and pi. So, and you can see the region is the curve, and y equal 1, that's y equal 1, and then x equal pi. So that's x equal pi. Okay, so that's the region they are talking about. So you can rotate this region about the y-axis. So you can rotate this about the y-axis. So once you rotate this about the y-axis, it's gonna reflect to the other side. So you get this, and then this one also reflect to the other side of the region. So you have this. Okay. I'm just drawing this for reference purposes only. What you need is you just need the two radii. Once you know the two radii, you can do it. But I'm just doing for completeness. Some of those information you really don't need. So this is like a negative pi on the other side. Good. So so we cut it. So that means this is a typical radius looks like. So we need to find the two radii. So one radii is the smaller radii, so which is so this is the smaller one. Go like that. That's a smaller radii, and you can see the larger radii is fixed. That's the larger radii, which is fixed, which is equal to pi in this case. Good. Now the question is how to find the smaller radii, and you can see that. So you need to solve for y, but if you solve for y, you really don't get what you need. So you have to be careful with this one because it's a special situation. So because if you try to, let's say you pick a y value, and if you try to invert it, which curve you get? So let's look at the situation here. So we have y equal sin x, and if you invert it, you get x equals sine inverse y. But you know the sine inverse is defined where the cosine positive. That means you really don't get what you need. So what you want to do is we have to use some geometry here. So see what we're going to do now. So we know that this is the x coordinate. So let's see how to use the geometry here. This is the x coordinate, and you can see that that's exactly equal to this value right here. If you look at the length, if you look at the lengthwise, they are the same by the symmetry. So that means to find r, what you need is you need to subtract, because we know that this is pi. Okay, this is pi. So that means to find r, what you need to do is so I'm gonna call so this is the x coordinate. So you can see what you need is if you call this length is the xr, if you call this length is xr, so that means the smaller radius is simply equal to xr, but to get xr, what you need is you need to subtract pi minus the x value. Okay, this x value, you subtract this x value, but that's equal to that x value, you subtract that one now. So that means small r is equal to pi minus x, okay, from geometry, but this x is equal to pi minus sine inverse y. So that is the difficulty here. So you have a different you need some nice algebra knowledge to do this problem. Okay, so that's the radius is pi minus sine inverse y. So that's a very special situation. Now we can write the formula. So v equal, after that we can do everything. So you can see this is a dy problem. It's again go from 0 to 1. So it is 0 to 1, and then the larger radius is equal to pi, so the pi squared minus the smaller radius is equal to pi minus sine inverse y squared dy. So that is what you get for as the setup of the integral. Good. I hope you learn a lot about how to handle these kind of situations. Okay, so what is more important is the first 30 minutes, and then you can look at those extra problems. Okay, so in the next one we can talk about the cylinders or the shell method.